Hey there, and welcome. Have you ever stopped to think about how things like your thermostat or even your car's cruise control just work? How they stay so perfectly steady? Well, it turns out they all rely on digital computers to wrangle our very messy, very analog world. So let's pull back the curtain on this hidden process that's pretty much running our lives. And really, that's the central puzzle we're tackling here. Think about it. The real world, temperature, speed, pressure, it's all smooth, it's continuous. But a computer, its brain only thinks in ones and zeros, right? In these tiny separate steps. So how on earth do you bridge that massive gap? How does a digital mind get a grip on analog reality?
The best way to think about it is like they're speaking two completely different languages. Over on the left, you've got analog. That's the language of reality itself, a smooth flowing wave, just packed with infinite detail. Then on the right, you've got digital. That's the language of the computer, all blocky, kind of like a staircase. It sees the world in these neat numerical chunks. And the whole secret to making this work, you have to be a really, really good translator.
Okay, so this diagram right here, this is going to be our map. I know, it might look a little technical at first glance, but the idea behind it is actually super simple. We're basically going to follow a single piece of information, one little signal, on its epic journey. It starts in the physical world, goes through the digital brain, and then comes back out to actually make something happen. All right, so where does our signal's journey begin? Well, it starts with the controller basically putting its ear to the ground. See, before a computer can even begin to think about the world, it first has to listen. And that whole process kicks off with something called sampling. And here's the key thing to get. A computer just can't watch a signal that's always changing, not like we can. So instead, it takes these super fast snapshots. We call them samples. It'll measure the value at one exact instant, turn that into a number, wait a tiny fraction of a second, and then bam, do it all over again, and again, and again, creating this long stream of data that's its best guess of what the real world looks like. But that, of course, brings up a really important question, right? If you're only taking snapshots, if you're only looking at specific moments, how can you be sure you're actually seeing the whole picture? How fast is fast enough to really capture what's going on? Let's walk through an example to see just how wrong things can go. So imagine this smooth wave here is the real signal we want to measure. Let's say it's the temperature bouncing up and down inside a reactor. Nice and clean, totally predictable. Okay, but now, what if our controller is a little lazy? What if it's only taking samples every once in a while? You can see the dots here. Those are our measurements. They're pretty far apart. But, at first glance, it doesn't seem so bad. We got some data points, right? Yeah, but check out what happens when the computer tries to connect those dots to figure out the trend. It sees this, a totally fake signal. It's much, much slower, and the computer has absolutely no clue that the original, faster wave is even there. This is a super dangerous illusion called aliasing, and it's the exact same reason wagon wheels in old movies sometimes look like they're spinning backwards. The camera's just not sampling fast enough.
Luckily, there's a golden rule for this stuff. It's called Shannon's sampling theorem, and all it really says is that to see a wave accurately, you have to sample it at least twice for every cycle it makes. Now, in the real world, engineers go way, way faster than that. But this theorem, it's like the fundamental speed limit for being able to see reality clearly.
Okay, great. So we're sampling fast enough, we're avoiding that aliasing trap. But we've got another problem. The real world is never this clean. It's noisy. So our signal's next big challenge is figuring out how to be heard over all that static. Yeah, this is more like what a signal from a real-world sensor looks like. All that jagged fuzz. That's electrical noise, maybe interference from other machines, or even just turbulence in a pipe. Now, if the controller tries to react to every single one of those tiny little bumps, it's just going to go crazy, constantly overcorrecting itself. It'll be totally erratic and inefficient. What it needs to do is ignore the static and just see the underlying trend. So how do we fix that? With something called a digital filter. And what's so cool about this is that it's not a physical thing you install, it's just a clever bit of software, an algorithm. The best analogy is to think of it like a pair of noise-canceling headphones, but for data. It's programmed to know what the real signal should sound like and just tunes out all that distracting static. And the effect is, well, it's pretty dramatic. On the left, there's our raw, messy signal coming in, and on the right, that's what comes out after it goes through the filter algorithm. Look at that, a nice, clean, smooth signal. Now the controller has a clear picture of what's really going on, and it can finally make a smart decision.
Okay, so let's recap. Our signal is now clean, it's accurate, and it has finally arrived at the digital brain. But here's the thing. Just knowing what's happening in this exact moment, that's not enough. To really be in control, a system can't just see the present. It has to be able to predict the future.
And before it does anything else, the controller has to answer what is maybe the single most important question in all of control engineering. Is this system stable? Or to put it another way, if I give this thing a little nudge, is it going to settle back down nicely, or is it going to spiral out of control and, explode? So to answer that life or death question, engineers use this incredibly powerful mathematical tool called the Z-transform. Now don't worry, you don't have to be a math genius for this. Just think of it like a crystal ball. It takes all the complicated physics of the system, how fast a valve opens, how quickly a liquid heats up, and it turns all of that into a simple map. And on this map, there are these special spots called poles. Where those poles land on the map tells you literally everything you need to know about whether the system is going to be stable or not. Here's how simple it is. The Z-transform draws a map, and the most important feature on that map is this thing called the unit circle. Now, if all of those poles we talked about land inside the circle, you're golden. The system is stable. Look at the graph on the right. If you give it a little kick, sure, it wobbles for a second, but then it settles right back down. It's predictable. It's safe. But, and this is a huge but, if even one single pole lands outside that circle, the whole system is unstable. And that graph on the right tells you the whole terrifying story. The tiniest little nudge will cause the output to just shoot off towards infinity. This isn't just theory. This is how bridges can collapse, how reactors can melt down. That's why this Z-transform map isn't some academic exercise. It is the mathematical safety check that prevents catastrophic disasters. It's absolutely critical. So, our controller has done its homework. It's listened to the world, it's filtered out the noise, and it's checked for stability. Now it knows exactly what action to take. The very last step is to turn that digital decision back into a real-world physical action, and finally, close the loop. And it happens in 3 really clear steps. First, the controller's algorithm does the math and spits out the perfect command, which is really just a number. Second, another translator, this one called a digital to analog converter or a DAC, takes that number and turns it back into something physical, like an electrical voltage. And finally, that voltage is what actually drives the hardware. It's what tells a valve to open or a motor to speed up. And that's it. That's the signal's entire journey, from start to finish. It began as a messy, continuous signal from the real world, got chopped up into numbers through sampling, was cleaned up by a filter, checked for safety and stability, and then finally turned back into a physical action to control that world. Pretty neat, right? So why should you care about all this? Well, because this whole elegant loop, this constant conversation between the analog and digital worlds, it's the hidden brain inside pretty much everything you use. It's in your phone, your car, it's running the entire power grid. It's the secret sauce that gives us the precision, the stability, and the efficiency that our modern world depends on. And that kind of leaves us with one last big thought to chew on. For decades now, we've been getting better and better at teaching machines how to sense, think, and act, how to control our physical environment with just mind-boggling precision. So the real question becomes, now that they've mastered that, what will they learn to control next?